Thank you so much for joining this lesson. We're going to discuss the Mokasa 1 2025 Physics Paper 2, the theory paper. So this is a joint examination which has been done by a group of schools that includes the Moi Girls Eldoret, the Kabarak High, and Sacho. So we're going to look at what they did in preparation for the KCSE 2025 so that we may also get equipped. So I invite everybody to this good paper. We're going to discuss it bit by bit until we get to know what was required for every particular problem in the paper. Remember to subscribe, remember to share so that you may invite some friends. As we continue learning, those in high school, I remind you of our program here, whereby you need to register with us for a very interactive program, STEM-oriented, that is mathematics and physics, then chemistry and biology, and I'm sure you're going to learn a lot. It will be very interactive. You'll be able to ask questions through Google Meet. You'll be able to answer questions, and you'll be able to get a lot of concepts clarified for you. And remember also our program here, whereby you can acquire airtime from any network, Safaricom, Airtel, Telcom, by just going to your M-Pesa menu, Lipa na M-Pesa. The pay bill number is already displayed here, 737356. Then the account number is the phone number that you're purchasing the airtime for, be it your own phone number for Safaricom, for Airtel, for Telcom, or even the number of a friend that you'd like to purchase airtime for. Then after that, you enter the amount, then you complete the transaction, and your airtime shall reflect instantly. So kindly utilize this facility and invite friends to the same. Back to the paper now. Physics paper 2, number 1. The figure below shows a ray of light incident on a mirror. Look at how incident it is, very perpendicular to the mirror. All right, part A, complete the diagram by showing the reflected ray. So this one being perpendicular, we know that it just goes through the same path. It goes back through the same path, just that. So you just need to show the arrow in the opposite direction. Now, what is the angle of reflection? You know, the angle of incidence is usually equal to the angle of reflection. So we must come from the angle of incidence so that we may conclude on the angle of reflection. Now, once the ray is coming perpendicular to the reflecting surface, we should know that in this particular case, the normal is usually a line drawn perpendicular to the reflecting surface. And this means the ray is also through the normal. And that means it's not making any angle with the normal. Therefore, the incident ray, in this case, is 0. And therefore, the reflected angle. Okay, the angle of reflection. The angle of reflection, let's call it that way, to be more exact. The angle of reflection, we can call it small letter r, is equivalent to 0 degrees. Yeah, there will be no angle of reflection. That is why it goes back through the same path. Look at part 2, still on the same branch of physics. Yeah, we are still dealing with light. So this is called optics. The figure below shows a graph of I over U, that is centimeters per centimeter, that is, against 1 over V, which is also per centimeter, because V is already in centimeters. When we take the reciprocal, then we should expect per centimeter for an object placed in front of a concave mirror. Concave mirror, very important. All right, so the graph is here. Then we are advised to do what? From the graph, determine the focal length of the mirror. This is a mirror, not a lens. Check some slight differences. The first thing that you do for such a graph is that you extrapolate the line to ensure that you cut the axis at some points. So you cut the x-axis and also the y-axis at some points. That's way. Like you can see for both axes, we are intersecting at 0.06. Therefore, ours is to ask ourselves, what is the relationship between 1 over u, 1 over v, and what we call the focal length? And we know that 1 over the mirror formula is equal to 1 over v plus 1 over u. Remember, 1 over v and 1 over u, any can come first. So we can use some fixed coordinates here, like at the vertical intercept. At the vertical intercept, which is 1 over u, that is a 0.06. At that point, the value of 1 over v is 0. Therefore, at that point, we say 1 over f is given by 1 over v is 0, but 1 over u is 0.06. So from that particular coordinate along the y-axis, we can get 1 over f being equal to 0.06. Then we can argue that f, the first value of f, or the first estimate of f, will be equivalent to, we take it, 0.06 reciprocal it is giving us 16.67. 16.67 centimeters. Then we can also take another estimation from the x-axis, whereby we say 1 over f will be given by 1 over v. So at the x-intercept, 1 over v is 0.06, but 1 over u is 0. So the second estimate will also be 16.67. In some experimental graphs, you discover that the value of the first f might be different from the second estimation. And that is where now f becomes the average of the two. So we take 16.67 plus 16.67, and we divide by 2, and that will give us f as 16.67. These are centimeters. That way. So for such a graph, and remember there are other graphs that may be used to determine the value of f, both for lenses and for mirrors. Please make sure you make yourself familiar to the interpretation of the graphs. So that is it. State the basic law of electrostatic charges. Unlike charges attract, like charges repel. Simple. Unlike charges attract, like charges repel. Simple. People should be very careful when stating these laws. Sometimes learners may confuse the basic law of electrostatic charges with the basic law of magnetism. So let people be very careful with what they are asked to account for. A positively charged rod is brought near the cup of a lightly charged electroscope. The leaf divergence first reduces, and as the rod becomes or comes nearer, it diverges more. State the charge on the electroscope. Now, the fact that the rod is positive, then as it comes to the cup, there is a decrease in the leaf divergence. Then it means the charges both at the plate and at the leaf. This one is the leaf. This one is the plate. So the charges at the plate and the leaf, it means they have decreased. You know, the divergence there is because of similar charges on both leaf and the golden leaf and the plate. So it means for a decrease in divergence, the charges which were there have been reduced. And so for them to be reduced, they must have been attracted towards the cap. And that means because it is a positive rod attracting them, then they are negative. According to the law that we have just stated, it simply means that these are negative charges. Explain this observation. So the electrons are attracted and neutralized. The electrons are attracted and neutralized. That is when it becomes exactly at the contact, because it's still being brought closer. Then we say that now the positive charges are distributed to the leaf and the plate, causing increase in the divergence. Causing increase in the divergence. Now we have some part of the electromagnetic spectrum here. The diagram below shows electromagnetic waves, detection, and uses. Fill in the blanks below appropriately. So we have X-rays, and we have the detector, possible detectors of the X-ray. Can be a fluorescent screen or a photographic film. So fluorescent screen. Then we have also photographic film. Photographic film, that way. Then they can be used on X-ray photography. That is what you know. Then now we are having a known type of radiation, which can be used for phototransition of blackened thermometer, can be detected by phototransistor of blackened thermometer. And among the uses is a warmth sensor. And definitely this is the infrared radiations. So the infrared radiations are used for warmth sensor. Radio wave signals can be detected behind hills. Look at that. Behind hills and in lower valleys, but TV waves cannot. Explain. What is, first of all, this behavior of waves being detected behind hills? This is called diffraction. The ability of waves to curve behind obstacles. So now we say that the reason why diffraction might be possible is due to a length of what we call the wavelength. But shorter wavelengths, you find that diffraction is not easy. Therefore, you say that radio waves have longer wavelength than TV waves. Radio waves, sorry. Yeah, let me repost the paper for you. Sorry for that inconvenience. Sorry for that inconvenience. Yes. So this is where we are. So we are saying that radio waves have a longer wavelength than TV waves, making the radio waves easy to be diffracted. Easy to be diffracted as compared to the TV waves, which have a small wavelength. Hence, they just pass without any diffraction. So the word diffraction here is very key. The length of the wavelength is also very instrumental in the answering of this. An iron rod is positioned facing the north-south direction and is hit several times. It was later observed that it attracted other smaller iron pieces. Use domain theory. Using domain theory, explain this observation. So this is because when the domains are hit, or when hit, the dipoles vibrate. When the iron rod is hit, the dipoles vibrate and settle, aligning themselves with the Earth's magnetism. Hence, gaining magnetism. So in case we hit this without the rod facing in the north-south direction, it won't gain magnetism. So it gains magnetism if it is facing in the north-south direction. Yeah, because it is having the dipoles aligning with the magnetism of the Earth. That is how the magnetism is gained. We call it the hammering method. Number 6, the figure below shows a current carrying conductor placed in a magnetic field. So this is current out of the paper. And here we know that magnetism is moving from north to south. That is how the magnetic field lines behave. So sketch the resultant magnetic field. Sketch the magnetic field between the poles of the magnet. Okay, so it's part of the question. So they will be moving here. The lines will be facing such a direction, that way. So that is what will be happening. It's good you show the direction using some arrows. Yeah, that is how the field lines will be moving. Then now show on the diagram the direction of the resultant force F. So the conductor here is going to move upwards. The force will take it upwards. Yeah, you can even use what you call the Fleming's left-hand rule, whereby you know that the first hand will show us the direction of the magnetic field. Then we will have the second finger showing us the direction of the current. Then the thumb automatically now will show us the direction. So the thumb will show us the force. So this is the left hand now. You are holding the fingers, the thumb, the first and the second, mutually at right angles. So we will have the second finger showing us direction of current, which is out of the paper. Then the first finger showing us the field, which is towards the right-hand side. Then automatically now the thumb will be pointing upwards. So that is how the force shall take the conductor. Number 7. The figure below shows a wave profile of a wave moving at a velocity of 200 meters per second. So we have the displacement there on the vertical axis. Then on the x-axis, we are having time in seconds. Determine its wavelength. Or the wavelength of the wave. Determine the wavelength, this particular wave. So from the x-axis, we can obtain what we call periodic time, the time to cover a complete wavelength. So if we move from 0.2, for us to cover a complete wavelength, we should be at the same position and moving in the same direction. So that will take us to this point. So from A to B, the time taken there, we call it the periodic time. We can also move, as long as we are considering two particles which are in phase, like we can move from C until we are at D. Yeah, point at D. We can also consider that. So what is the time difference taken there? From 0.06, 0.02, we have 0.04 seconds. This is the periodic time T. Yeah, alternatively, we can use 0.08 minus 0.04. We get 0.04. So the periodic time is 0.04. Then there's something called frequency. Frequency and periodic time are related such that one is the reciprocal of the other. So for us to get F, we need the reciprocal of 1 over 0.04. So what will be this? What will be the frequency in this case? And we're getting 25 Hertz. Yeah, 25 Hertz. Then something else that we're supposed to know is that we can also calculate. Now we needed the wavelength. So we know the general wave equation, which says that velocity is given by F lambda. Frequency multiplied by wavelength. So frequency of 25 and a known wavelength are supposed to give us 200. So how do we remain with wavelength? By dividing by 25 through, and the answer becomes 8 meters. Yeah, the units of wavelength are meters that way. Then in number 8, we are told to distinguish a transverse wave and a longitudinal wave. So we say that the main difference now in transverse wave, let me even write it, in transverse wave, the direction of particles, the direction of, or the vibration of particles, direction of particles is perpendicular to the wave motion, while in longitudinal wave, the vibration of particles is parallel to the wave motion. There are some other differences or some other distinction between the two waves, and is in that a transverse wave is characterized by what we call crests and troughs. As you can see in this, these are crests, these are trough and a trough here, but C and D are what we call crests. So a transverse wave is characterized by crests alternating with troughs, while for longitudinal waves we have rarefactions alternating with compressions. The rarefactions are called low pressure zones. The rarefactions are the compressions are called high pressure zones. So high pressure zones are called compressions. Low pressure zones are called rarefactions. So this is leading us now to part B. This is part B of number 8. Yeah. The figure below shows a longitudinal wave. Yeah, you can see it's characterized by low pressure zones or low pressure areas or regions, which are called rarefactions. Then high pressure are called compressions. Now, the high pressure ones, we have the particles squeezed. So this is a high pressure. A high pressure region. Then where particles are spaced, this one's a low pressure. It's a low pressure region. So we just needed some examples. Yeah, that way. A student was investigating the brightness of bulbs when set up in electric circuits. She used identical bulbs and cells. The circuits A and B were what she set up. We can see A, whereby the bulbs are in series with one another. Then look at B, whereby the bulbs are parallel to one another. And actually, it is a preferred set of it's a preferred arrangement of bulbs in the domestic wiring for reasons known. Like in case one goes off, the other one can just, in case one blows off, the other one will just continue working. Unlike in the series connection in part A, whereby in case one goes off, we shall have the other one automatically stopping the function because they are in series. Which setup was the bulb brightest? And this is going to be B for me. Give a reason for your answer. We have a little, we have in B, there is reduced internal resistance. You know, each bulb is having its own internal resistance. So when arranged in series, the internal resistance, the effective one, will be summation of the resistance for both. But in B, it will be 1 over R plus 1 over R equals to 1 over R total. So you discover this one is going to be little. In this one, R total equals to the first one plus the second one. So in A, it will result to a very high value of internal resistance. But in B, internal resistance is reduced. Remember to subscribe to this platform as we transition to section 2 of the same. Remember our consultation line is 0704 153366. Okay, number 10, which is the first question in the section 2. Define interference of waves. And this is what we call the merging of waves. The merging of two waves. The superposition, in other words. The superposition or the merging of waves. We know this can lead to either a bigger wave or a smaller wave or no wave at all. When we say no wave at all, that is called a standing wave or a stationary wave. When we talk of a bigger wave, that is a constructive interference. When you talk of a smaller wave, that is destructive interference. All right, look at part B. The figure below shows the rays of monochromatic light incident on two adjacent slits, S1 and S2. We have the monochromatic source of light. Then we have the two slits, as you can see. Then there is the screen. There's the screen there. What is the purpose of having slit 1 and 2? This is to ensure that we produce a coherent source of light. So this is to produce a coherent source of light. Yeah, the next thing you should be asking yourself is, what is a coherent source of light? Because the examination can go to that extent of asking, what do you understand by coherent source of light? This is a source of light such that the light wave produced, the light wave produced is having the same frequency, the same wavelength, and in phase, such that now we can have what we call now the interference occurring. So that is why the slits are vertically above one another and not one ahead of the other, and such, to ensure that they are coherent. Same frequency, same wavelength, and in phase. State and explain the observation made on the screen. So when now we produce some light from here, we'll also have some other light from this other source coming out. And as they continue, we will have the mergings happening. The merging will be happening. So you're supposed to know that at the end of the day, by the time they are reaching at the screen, this one is the screen. By the time they are reaching at the screen, you'll be able to see dark fringes alternating with bright fringes. So you'll see dark fringes alternating with bright fringes. Bright fringes. So we say the dark fringes. The dark fringes are as a result of destructive interference. Destructive interference, while the bright fringes are as a result of constructive interference. Yeah, constructive interference. In case the experiment for interference is done using a sound, whereby two speakers are placed in front, then an observer passes through a path like A, B. What alternates in that case is loud and soft sounds. And the loud sound is due to constructive interference, the soft sound, destructive interference. State what is observed on the screen when, part 1, the slit separation D is reduced. So when the slits are brought closer to one another, what do you expect? And it is that the fringe separation reduces. The fringe separation reduces. You said the original observation is that we are having dark fringes alternating with bright fringes. So now they will be closer to one another more. They'll be more closer to one another. They'll be closer to one another. Okay. The distance D is increased. When you increase the distance now from the two slits to where the screen is, the fringe separation increases. The fringe separation also increases. Then in part 3, white light is used. In case white light is used, we are going to see a band of light, a band of the 7 colors of the rainbow. A band of the 7 colors of the rainbow. So we are going to see the spectrum of the rainbow, because the white light will be split, the splitting of the white light. Okay, the dispersion of white light, that is, the dispersion white light. Give an expression for the path difference if the first bright fringe forms at P after the central bright fringe. Okay, so we are going to express an expression for the path difference if the first bright fringe forms at P after the central bright fringe forms. So that will be from the slit 2 to P minus slit 1 to P. That will give us the wavelength. That is going to give us the wavelength, or the one wavelength. Because we need, from the time we are seeing a bright fringe to the next time we shall see a bright fringe. Well, look at number 11. Define critical angle. Define critical angle. So critical angle is usually, this is a word which is used during what you call total internal reflection. And I'm going to illustrate it a little bit. So if we have medium 1 and medium 2, then are such that no, this is the normal. So if a ray is moving from the medium 1, medium 1 is less dense. Yeah, medium 1 is less dense. Then we expect in the denser medium the ray of light to be reflected away from the normal that way. So this can continue until we increase the angle of incidence. As the angle of reflection changes, it reaches a point whereby it moves along the interface, making the angle of incidence 90. So at that point, where the angle of incidence, the angle of reflection in the denser medium is becoming 90, then the corresponding angle of incidence is what you call the critical angle. And beyond that, if we increase the incident angle beyond that now, there will be no reflection, there will be no refraction, there will be total internal reflection. So we say that a critical angle is the angle of incidence in the less dense medium. In the less dense medium, for which the angle of refraction in the denser medium is 90, for which the angle of refraction in the denser medium is equal to 90 degrees. Yeah, that is the definition of what we call yeah, that is what you call a that's what you call critical angle. Now, a student sorry, let's look at something here. We want to see whether in the definition of critical angle there is something I'm leaving out. The angle of incidence in a denser medium, at which the angle of refraction in the less dense medium is 90. The angle of incidence in the denser medium, we can have a, let me show more illustration on the same so that we may get to the exact definition. We may have a ray of light moving from glass into air. Glass is optically denser. Actually, there is the word optical density, which we are leaving out, because optical density is different from density. So this is the angle of incidence. And we are saying that from optically denser medium to optically less dense, we have the refraction happening away from the normal. This is the normal. So away from the normal means there is a point where the angle of refraction here shall become 90. So at this point, we are saying that the angle of incidence now in the denser medium is now what we are calling the critical angle. So at this point, I is given a special name, which is critical angle. Therefore, the definition of critical angle is the angle of incidence in the denser, in the optically dense medium, for which the angle of refraction in the less dense, actually in the optically less dense medium is 90, optically less dense medium. So beyond critical angle, we usually have total internal reflection occurring. So if we increase I beyond critical angle, we will not have further refraction. It will be internal reflection in the first medium, which is denser. Yeah, in the first medium, which is now denser. Therefore, a student had a research project of making fiber optic cable as shown. Then we have a medium A and B. Then we are asked, compare with reason the optical densities of materials that is making A and B. So when the ray of light reaches the medium B, it is supposed to be totally internally reflected. Totally internally reflected without passing through to get reflected. So we will not have refraction, but internal reflection throughout the fiber until the light comes out. We will have what we call total internal reflection that way. Therefore, for total internal reflection to occur, these are conditions now necessary for total internal reflection to occur. The ray of light must be moving from the denser medium to the less dense medium. And that means A will be denser. A is optically denser. We are comparing optical densities. A is optically denser. A is optically denser than B. And this ensures total internal reflection of the light. Yeah, to ensure total internal reflection of the light, then we should have A being optically denser. On the diagram, draw the path of ray of light incident on the cable at P till it emerges outside at Q, till it emerges at Q. And that is how it shall behave. So I've already drawn to illustrate. So just observe it. So it will be that way. That is how it shall behave. So that is how the ray of light behaves until it emerges out. All right. Now look at this. The figure below shows a ray of light passing into a glass prism, ABC. You can see the glass prism. It is right angled at one point, meaning that the other side here, because we are already given 30 degrees, then this is automatically 60. Now, if a ray is incident at a medium, and this is at 90 degrees, then we should know that it will pass undeviated. The ray passes undeviated. So it will just proceed to the boundary, which is a CA. So it just passes like that. You know, we've been taught to sketch the path of the ray as it travels from the face of AC until it emerges from the prism. Critical angle of the glass is 42 degrees. Show all the angles. Show all the angles. It is also good to indicate arrows of the rays. So once it reaches at that face, we can draw a normal at that point of incidence. It's good for you to know that this shall be 30, meaning that the angle of incidence here is 60 degrees because the normal is perpendicular. Then we can see that, you know, we're told that the critical angle of glass is 42, and the angle of incidence is already greater than critical angle. Actually, in case we had gotten an angle of incidence, this is the angle of incidence, if we had found it smaller than 42, there would have been reflection, something called refraction. Refraction instead of the reflection that we're going to see. So now it will be reflection. So we will have the ray being we will have the ray living through 60. And remember, if that is 60, then it means, yeah, because the angle of reflection must be equal to the angle of incidence. So we still have another 60. So we expect a 60 at this point. But the point is, total internal reflection will have occurred. If that is 60, then we are having a 30 here. And if we are having a 30 there, we are supposed to make what we are calling draw another normal there. So when we draw a normal there is something we're supposed to ask ourselves. What value of angle is that? What value of angle is that? On this side, we are having 90. Then we are having a 30 and 30. That is 60. If that is a 60, then it means the angle at this point is 30. If the angle at this point is 30, it is our angle of incidence now. And if that is our angle of incidence, then it means the angle of incidence for this particular face, which is AB, Now the angle of incidence is becoming smaller than critical angle. Therefore, there will be no total internal reflection. And now that the ray will not be reflected internally, it has to be refracted outside. So it will pass through. It will pass through now from the denser medium to the less dense. Even if we don't know the angle here, it shall be reflected away from the normal. So that is what you should know. The reflection will be away from the normal. Yeah, away from the normal that way. So that is how the reflection shall occur. That is how you're supposed to show the ray of light. So you should be in a position to sketch the path of the ray or through. Number 12. The figure below represents two parallel plates of a capacitor separated by a distance d. Each plate has an area A, which is in square units. Okay. Suggest two adjustments that can be made on the plates so as to reduce effective capacitance. To reduce on effective capacitance. Remember, capacitance is directly proportional to area of overlap, and capacitance is inversely proportional to distance of separation. So for you to reduce capacitance, then increase distance. So move them away from one another. Away from one another to increase distance d, the distance of separation. So when the distance of separation is increased, capacitance will be reduced. Then we also say that capacitance increases with area of overlap. Area of overlap. So you can move them sideways or move one sideways. Move one sideways. To decrease the area of overlap, because the greater the area of overlap, the higher the capacitance. But now we want to reduce it. So you must be very keen on the way the question has been put. This time around, we are reducing the effective capacitance. Some other questions will just go direct to ask you, what are the ways that we can use to increase? Okay, what are the factors affecting capacitance? Whereby you just talk about area of overlap and distance of separation together with the dielectric material. But this time around, we are affecting the capacitance negatively. Now we have a figure here showing three capacitors. We have the 3 microfarad, the 2 microfarad, and the 4 microfarad. Determine effective capacitance of the arrangement. The first two, the 3 and the 2, this one, are parallel to one another. And when they are parallel, effective capacitance there should be 1 plus the second one. So for the 2 parallel, we just need 3 and 2 added to give us 5 microfarads. Then effective capacitance, when they are in series, you know now, 3 and 2 can be represented by 5 microfarad. Then it is in series with the 4 microfarad. So we are talking about a 5 microfarad capacitor and a 4 microfarad capacitor, because we have reduced the 3 and the 2 to 1. All right, now from there, we will say that effective capacitance now effective capacitance shall be 1/5 plus 1/4. Then we take the reciprocal because they are in series, or 1/C total is given by the first capacitor plus the second capacitor reciprocal. So after adding the fractions, or after adding the reciprocals, we are expected to find again the reciprocal now for us to arrive at the answer. So effective capacitance shall be 2.22 microfarads, or 2.22 times 10 to the power of -6 farads. We make them as a unit now. Find the total charge. You know that charge is given by CV. So charge will be C. Charge is going to be C, which is a 2.22 multiplied by 10 power -6 multiplied by 6. Let's check that multiplication. Let's check that multiplication. When we talk about 2.22 times 6, so I'll get 1.332 times 10 power -5. Being charged, we can talk about coulombs. Yeah, being charged, we talk about coulombs now. What about the third question here, which says, determine the potential difference across the 2 microfarad capacitor. Across the 2 microfarad capacitor, we usually say that charge behaves like current. When in series, it passes through uniformly. When in parallel, it is split depending on resistance. Therefore, the total charge in the system will pass through here. So we can first use the 4 microfarad capacitor to know the potential difference there. What will be the potential difference at the 4 microfarad capacitor? You know, potential difference is given by charge over capacitance. Therefore, voltage at the 4 microfarad capacitor shall be total charge passes there. So 1.332 times 10 power -5. This one will be divided by the capacitance, which is 4 times 10 power -6. So what will be the potential difference here? So we divide this one by 4, and we are getting 3.333 volts. Therefore, now the other voltage from the total is the one which will proceed to 3 and 2, and it will do so equally. So the potential difference at 2 microfarad capacitor shall be 6 minus 3.33. So 6 minus this value, we are getting 2.67 volts. Yeah, 2.67 volts. And now that it is a parallel setup for 3 and 2, the potential difference shall be the same. So if we have potential difference for 2 microfarad capacitor, we can get potential difference across. Actually, that is what we wanted. We are through. That is it. We are actually through. The potential difference across the 2 microfarad capacitor. We are already through. I thought we are getting the charge stored there. Yeah, so this is it. Then the last part of this question, which is part C, state one application of capacitors. We have a rectification in the diodes. There are several applications. We also have flash cameras, can be used in flash cameras. We can also have a reduction of sparking in induction coil. They are used to reduce sparking in the induction coil. Okay. Number 13 in section 2, state Faraday's law of electromagnetic induction. So the law says that the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linkage. The magnitude of the induced EMF, the magnitude of the induced EMF is directly proportional to the rate of magnetic flux linkage. Yes, the rate of magnetic flux linkage. Let people beware of a statement of laws and principles and rules. We are not going to avoid that in physics. You must state a law in one way or another. Yes, part B. A single coil of wire is held between the poles of a magnet as shown in the figure below. Yeah, this is the wire. This is the magnet 1, the magnet 2. Then we are told further that the ends of the coil are connected to a sensitive galvanometer. When the coil is slightly rotated clockwise about its axis in between the magnet, the galvanometer deflects. On the diagram, indicate the direction of flow of current. Therefore, when this one is rotated in the clockwise direction, now it has to be made to spin in a clockwise direction. And already we are able to see that a magnetic field is already moving from where the north is to where the south is. Then the direction of the current will be moving in this direction. So that's how the current shall flow. Yeah, that's how the current is going to flow. That is how the current shall be flowing. So we have shown the current in the conductor. So the conductor is usually moving fast so that it may, remember when we were discussing a magnetic effect of an electric current in section 1, it was a current flowing through a magnetic field so that a force is introduced on the conductor. In this case, we are introducing a force to the conductor, which is already inside a magnetic field for current to be introduced. This is what we call now magnetic flux linkage. Are we together there? So please, you must be able to note that difference. This is actually, there is a very wonderful relationship there between what we did in Form 2 work and what we're doing in Form 4 work. In Form 4, in Form 2, we add current moving to produce a force. Now in Form 4, we have the conductor moving to produce current. So the conductor is moving in a magnetic field. Previously, we had current moving in a magnetic field. And in either cases, we have a force being produced, and here it is a force producing current. So force is producing current. In form 2, current produced a force. That is it now. So in part 2, explain why the galvanometer deflects. So the galvanometer is going to deflect because the conductor is cutting the magnetic field, and the change in flux is inducing some EMF, and hence current flows. So we say that the conductor cuts the magnetic field, inducing an EMF. The conductor cuts the magnetic field, inducing an EMF. Inducing an EMF. State and explain how the deflection will be made larger with the same apparatus. So with the same apparatus means there is no change in the magnet. Yeah, so we cannot say using a stronger magnet. In this case, we are limited to the magnet that is already available. So we should be talking about now increasing the speed of the conductor. So when you twist the conductor at a faster speed, we have the rate of flux linkage increasing. So we can have increasing the speed, the rate of magnetic flux linkage. So increase the speed of rotating the conductor. This increases the rate of magnetic flux linkage, and hence the deflection will be greater because there will be a bigger EMF induced. The diagram below shows an induction coil used to produce sparks in the car ignition. Explain how the sparking is produced when the switch is closed. So when you close the switch here, it's a small process. Remember, we say the soft iron rods are magnetized, attracting the armature. The soft iron rods are magnetized. They are magnetized, making them to attract the armature. Making them attract the armature. They are used as soft iron rods because a material of iron is a soft magnetic material, very easy to magnetize. So immediately you close the switch, current flows, magnetism is introduced or is induced the soft iron rods. This breaks the contact and armature returns to its original position. This breaks the contact and the armature returns to its original position. It returns to its original position. Then we say the contact is made again and a larger EMF is induced in the secondary coil. The contact is made again and a greater EMF is induced in the secondary coil. In the secondary coil. This is the one now which leads to the sparking now. So sparks is created at the sharp points igniting petrol air mixture. Spark is created at the sharp points. Spark is created at the sharp points igniting the air petrol mixture. The air petrol mixture. So that is what exactly happened. Remember, the sparking can be minimized by, what we have just mentioned, the application of capacitors. We have already mentioned that application of capacitors will lead to reduced sparks. So we also taught to state the purpose of the part labeled B. The part labeled B. The part labeled B is already, actually I didn't know whether it's part of that question, but you can see now that is a symbol of a capacitor. So it's a capacitor which reduces the sparking. It's a capacitor. This one minimizes the sparking. It minimizes the sparking. Number 14 is on mains electricity. Electrical energy is distributed in the grid network using thick aluminum cables as alternating current at high voltage. Explain why. A grid system is important. This ensures that there's continuous supply of electricity, even when one branch has failed, because all electricity is fed into the system. Then now from the system, from the grid system, it's now distributed to all parts of the country. So it ensures continuous supply of electricity, even when one plant has broken down. Ensures continuous supply of electricity, even when one plant has failed. So even if one site which produces electricity fail, there will be a particular area which is disadvantaged, because all electricity has to be brought to one point, then supply is made from there at a very high voltage. So current is supplied at high voltage to minimize what you call power losses. To minimize power loss through the cables. The power is transmitted as alternating current voltage. So this is to ensure that it can easily be stepped up or stepped down. Yeah, it can easily be stepped up or stepped down. So this allows the stepping up and stepping down. This allows stepping up and stepping down of the voltage. Remember, voltage has to be stepped up transmission and stepped down to consumable values by the final consumers of the voltage. Why do we have the core laminated, the aluminium core, which will transmit the electricity? Why is it laminated? And this is to prevent power losses. To prevent power losses. Actually, we call them eddy currents. So this one prevents or simply minimizes eddy currents. So to reduce power loss by eddy currents. We have a figure here. The figure below shows part of domestic wiring system, which with a fault. A fault is a mistake. So let's look at it. So we have the live wire. Then we have a fuse connected. Then we have the electrical appliance here. Then we have the neutral. And now this is a switch. Identify the fault and draw another diagram beside with the correction. So the fault here is the switch has been connected. The switch has been connected to the neutral. It should be connected to the live. Therefore, switch connected to the neutral. Switch on the neutral wire. That's a fault instead of the live. So it should be this way. The switch there. Then we can have the fuse. Then the electrical appliance. Now this one comes to the neutral. This is the live. So that's how the connection is supposed to be. State the function of the part labeled F. I said F is a fuse. This one safeguards electrical appliance from excessive currents, actually from blowing off. So it prevents electrical appliances from damage caused by excess currents. Safeguards electrical appliances from blowing off due to excess currents. Due to excess currents. Yeah. Due to excess currents. That way. Part C. The following electrical appliances were used as follows in a certain home. A 2000 watts water heater for 2 hours per day. Then a 75 watt bulb for 10 hours per day. Then we have a 1500 watts electric iron for 1 hour per day. Calculate the number of kilowatt hours used for 30 days. That is one math. Then the cost. Okay. Then the cost. Let's see the number of kilowatts and the hours. From the first appliance, which is the heater, we are talking of 2000 watts, which is 2 kilowatts, then multiplied by 2 hours. So there we get 4 kilowatt hour. Then from the 75 watts bulb, it's 0.075 kilowatts. When you divide by 1000 to get kilowatts, then this is supposed to be multiplied by 10 hours a day. This is supposed to give us 0.75 kilowatt hours a day. Then we have a 1500 watt bulb for 1 hour. So this is 1.5 multiplied by 1 hour. per day. We are getting 1.5 kilowatt hours per day used. So total per day shall be 6.25 kilowatt hours. This is per day. What about for 30 days? So for 30 days, we shall have 6.25 multiplied by 30. Yeah. So multiplied by 30, we're going to get 187.5 kilowatt hours. 187.5 kilowatt hours. So we have to convert it to the units which measure the electrical usage, whereby we convert power into kilowatts, then multiplied by time, and the time must be in hours. So we have the hours per day, so that we get the total power or the total units per day. Then for the 30 days now, we have to multiply by 30. So we get that. The cost of electricity in 1 month, if the company rate is 12.50 per unit. So we have to take now 187.5 and we multiply by 12.50 so that we know the amount in the 1 month of 30 days. So 187.5 multiplied by 12.50. This gives us 2,343. 2,343.75 Kenya shillings. Yeah, Kenya shillings. That's it. Look at number 15 now. We are back to light again. Back to light. Form 4 work now. Whereby we'll be dealing with lenses. The first question, distinguish between a real and a virtual image. So a real image is made by the intersection of real rays, while a virtual image is made by the intersection of virtual rays. Yeah, by the intersection of virtual rays. There is a figure here, whereby we're told that the figure below shows an object O in front of a lens. So we have a lens, and looking at the lens, it's what we call convex. So this is a convex lens. You're supposed to be very careful. Convex lens, which is also called converging lens. So you're supposed to take the sample of the lens very carefully, because it is the one that will determine how the rays behave. Will they be converged? Will they be diverged? Then we have the first question there. By drawing appropriate rays on the same figure, show the position of the image formed. So we're supposed to know that there are some 3 important rays. One is a ray which is close and parallel to the principal axis. Such a ray is always converged through F for the converging lens. But for the other type of lens, it is supposed to diverge from F. So this ray now, after refraction, it is supposed to go through F. Yeah, the ray goes through F like that. Then there is another ray which passes through the optical center of a lens, and such a ray passes undeviated. So if a ray goes through the optical center, it will pass through undeviated. So we can do a second ray through the optical center. Now this is the optical center. So a ray through the optical center passes on undeviated. If that is so, then it means the two rays are intersecting at this point and they are real rays. So we will have a real image forming here. So that is where the image position is going to be. Remember, the drawing of rays is supposed to be accompanied by arrows. Yeah, that is it. In part 2 of this question, what are we talking about? An object is placed 20 centimeters in front, 20 centimeters in front of a diverging lens, of focal length 10 centimeters. Determine the position of the image. Very interesting. It's the diverging lens thing. If the focal length of a diverging lens is given, then you're supposed to know that it should be given a negative sign. The F in this case is going to be negative 10. Then object is placed 20 in front. So that is U, object distance 20 centimeters. Now, the reason why we allocate a negative to the focal length of a diverging lens is that the principal focus of a diverging lens is usually a virtual point. That is where rays appear to diverge from. If they just appear to diverge from, then it is not a real focus. And so the distance from such a focus to the optical center of such a lens will also be treated to be a virtual distance. And that's why we are giving it a negative. So we know that 1 out of F is usually given by 1 over U plus 1 out of V. In this case, it is 1 out of V, which is unknown. So 1 over V can be given by 1 over F minus 1 over U. So we need to say that 1 over V, I've made it the subject in this formula, equals to 1 over F. So 1 over negative 10. So negative 1 over 10. Then minus 1 over 20. Yeah. So how do we get 1 over V? We're now supposed to take 1 over 10, 1 over 20. Is going to be negative 3 over 20. So if 1 over V equals to negative 3 over 20, then V itself shall be the reciprocal. It shall be the reciprocal. Therefore, this becomes negative 6.667 simply, which means the distance is 6.67, only that the image is virtual. And that is why the negative is so clear. That is why the negative is very clear. So the negative is here to mean that the image is virtual. Image is virtual. That's what you're supposed to learn from such a sign. All right. All right. All right. We are in page 10 over 10. Remember, we are just finishing up with this. The figure below shows how a distant object is focused in a defective eye. So a distant object cannot be focused well at the screen. We have the rays meeting between the eye and the retina. So if a distant object cannot be seen, it means this eye can see a near object. So this one is called short-sightedness. State the nature of the defect. Short-sightedness or short sight. The name is also called myopia. Now, if we add a near object not well focused, then we would say this is a long sight. or long-sightedness or hypermetropia. But this time round, we are talking about myopia. On the same diagram, sketch the appropriate lenses or the appropriate lens to correct the defect, and sketch rays to show the effect of the lens. So if rays from a distant object cannot be focused, they are meeting before the retina, we are supposed to use what we call a diverging lens to ensure that the rays are diverged and have them meeting at the retina. Therefore, we use a diverging lens, which is otherwise called the concave lens. So the concave lens will be used, and it will make these rays, which are from a distant object, they will start now behaving as though they come from, they will start behaving as though they are coming from a point, because they have to appear to be diverging. The object has to appear now as though it is here. And now the rays will be able to be focused very well. The rays will be able to be focused very well at the retina. So this effect now will make the rays to go all the way to the retina without intersecting anywhere. That way. So the rays will be able to meet comfortably at the retina when such a lens is applied. So that is the effect it will have. So that is the end of the paper. Thank you so much for following. Remember our consultation line 0704 15 33 66. So that is it. Thank you so much. See you next time.